All right, it's time. I'm not going to use this. Drawn out how Android renders the UI by Chet, Haase, and Romain.
Don't clap yet. You haven't heard what we've had to say. Thanks for coming to the talk. We do have multiple titles here, but basically it's all about how we get from the UI that you see on the screen into the pixels that actually produce that UI. I'm Chet Haase.
And I'm Romain.
And we like to talk about rendering. We did variations on this theme about 4 and 5 years ago, and then we thought we were done. But enough things have changed in the system, and there are enough details that we thought it might be interesting to go through it again and remind ourselves how everything works, as well as tell other people about it.
And we're also going to go into details about parts of the rendering pipeline that I don't think we've ever mentioned in previous talks.
Secret parts of the pipeline. This is not a talk where we're going to tell you how to use the APIs. So this is not, how to call this to be more optimal. But like a lot of the things that we do, with the podcast or the articles or videos or whatever, we believe that having a good mental model of how Android works as a platform is helpful to developers. If you know how the system works, then when you see problems in profiling or whatever, then you can try to figure out what's going wrong. So let's go. A lot of slides. We better start. Rendering could be defined as melting fat in order to clarify and condense it. That's not actually what we mean today. We mean turning a UI description into the pixels on the screen. So actually drawing those things on the screen.
And before we get started, we just wanted to mention that this is only a 50-minute talk. To go into deep details about the entire rendering pipeline, we would need several hours. So a lot of what we're going to show you and a lot of things that we're going to explain are not exactly how things work, but they're close enough to reality that they match. But if you go read the source code, you'll see that things are way more complicated than they will appear on the slides. So just be prepared if you ever go look at the source code of the platform. The other reason we wanted to talk about this, so Chet mentioned that things have changed on Android over the past few years. And we've worked ourselves on the rendering pipeline. So when I joined the Android team, one of the first things I did was optimize the invalidate and drawing system. We're going to talk about this in details. And Chet and I wrote a hardware rendering pipeline for Honeycomb. And over the years, we implemented a number of the optimizations that we're going to talk about in this presentation.
All right, so we're going to have a series of dots on the top of the screen that show the various phases of rendering. So we're going to sort of walk through all the different pieces now, and then you'll have this little visual reminder as we go through a lot of details in the presentation. So first of all, you have the choreographer, which is going to send a vertical sync pulse up to the UI and say, OK, it's time to start doing stuff. This happens on most devices 60 times a second. So the vertical sync is the time when everything basically starts for the frame. And then the goal is to do everything that your application needs to do to display that frame's information on the screen within that little window, which is 16.666666 milliseconds. OK, so there's a vertical sync. That gets sent up. And then the next phase is input. So this is where the user did something with the screen that's trapped at the native level and then sent up to the UI thread level where we process that information. We want to take those input events and do something with it, move the list, click the button, whatever that is.
And I mentioned we're not going to go into the full details of every step. So for instance, the input step itself can be very complicated. We have to go through the entire view hierarchy. We have to process the move event, the up, the downs, compute velocities. We're not going to talk about any of this here.
The reason he keeps saying this is because it's going to get really complicated here very soon, and we want to assure you that it could get a lot more complicated.
Well, Chet find it complicated. I'm sure you won't.
OK, so after input, we process animations. So we do a lot of animations by animating properties of views. So this is the time when we see what those properties changes are and what we need to do to react to them, how it affects rendering.
And animations is another interesting step. So here we're focusing on the hardware accelerated pipeline, and we're also talking about the new animation system, not the old one that you can find in the android.view.animation package.
You can find it there, but please don't use it there. Measure and layout. touch. These are two steps that always go together. We'll get into those later. After the layout processing, then we actually draw the views. This is the process of turning the description of what those UI elements are into the actual commands that are going to draw them.
Yeah, and don't be fooled, the draw phase that we see here is not when we actually draw on screen. It shouldn't be called draw at all.
But I'm going to call it draw anyway. All right, then we have a sync phase. We have two threads that are responsible for the rendering. There's the UI thread, where most of the stuff happens, and then there's the render thread, which is responsible for talking to the GPU. So the sync phase is responsible for taking the information from the UI thread level and passing it down to the native render thread. After the sync phase comes the execute phase. We turn one description into a different description of operations and parameters. We get a buffer from Surface Flinger so that we can actually put commands into it. Then we issue commands. This is actually talking OpenGL. So we're going to talk to the GPU at this point. Then we swap the buffer. We say, OK, we're all done drawing the frame. Now go ahead and do what you need to display it on the screen. And then there's the composite step, where the pixels actually appear on the screen. So we'll walk through most of this in the process of this talk today. OK, so there's all the dots on top. There's the information. And here's a very simple example. I wrote this program right here. I'm not going to run it for you. I'm just going to show screenshots because it's too complicated to run.
And you had so many problems writing this app.
OK, so simple recycler view thing. It's got some items in there, which you can tell because they all say item. We're going to have a couple of different variations to show you what different things can happen during invalidation and layout. So the first one, very simple example. The user clicks one of these items, and that causes us to change the background color. No idea why you'd want to do this in your program, but that's what I wanted to do in my program. So then it ends up looking like this. Pick a random color, and that shows up at the background as the background of the item. The layout that I have for this application, that's a lot of lines of code, but basically it's just a constraint layout, which is what Android Studio gives you by default. And then inside of that, we have a recycler view taking up all that.
And this is a perfect waste of a constraint layout. If you only have one child that takes all the space, you don't need constraint layout. But Chet doesn't know better. There's a talk about constraint layout this afternoon. You should go.
I should totally go. All right, so the view hierarchy, if you ran a tool called Hierarchy Viewer, or this has actually been updated in Android Studio, there's an integrated tool called Layout Inspector, then you would see something like this. Different representation of it, but it'll show you all the views that exist in your activity. Now, most of those views you didn't directly produce. We produced them on your behalf. Things like the thing at the very top, the decor view, a lot of views for action bar, so that you get the split action bar at the top, and then the content view that you have. What your activity code actually produced was the stuff that's put into the content frame layout there. So that's the subtree that your activity is going to directly affect. And then everything else is more sort of at the system level that you don't directly touch. All right, so let's walk through what actually happens here. The user presses, right? So they have clicked on that thing, and then we're going to process the click event. So we come in with vsync. That's going to say, here's an input event. It's time to do all the input and animation processing, that stuff that we talked about. So it is processed as a click, which means it calls into this code. Eventually, the item clicked code, which I have in my awesome demo. In the item clicked method, we set the background color to this random thing here for no particularly good reason. And that will end up calling into the set background color of view, which does a bunch of stuff, and then it calls invalidate. Invalidation is the process of telling the tree that it needs to redraw stuff. It does not actually redraw. It just says something needs to be redrawn, and it propagates it all the way up. There's a really good reason why invalidation is separate from actually drawing, because there may be several things going on that invalidate, and we don't want to redraw everything that we need to on every one of those. Instead, we just want to propagate the information that something has changed, and then after all that stuff propagates, then there's another phase that actually handles rendering it. So there's a click that results in, let's see.
You should describe what's going on for people in the back.
Yeah. I'm trying to figure out where the invalidate calls. OK. So we set background color on the item down here, and that called invalidate on that view. And that invalidate results in walking up the tree all the way up to the top. So it's going to call a method along the lines of invalidate child. Again, there are more details to this if you really want to know the real method names, but it's going to propagate that all the way up, not invalidating every view, but rather passing the information that a view somewhere in the tree has been invalidated, and all the parents need to know, because at the top level of the tree, we're going to need to track that and then walk our way back down and redraw what we need to. So we walk it all the way up. Look at those animations. Very impressive. OK, so there's a class called viewRootImpl. If you ever poke around the source code, big class, a lot of stuff going on there.
You probably don't want to go look into that class, but it's basically the class that's responsible for everything in your application. It creates the window, it creates the underlying surface, it creates the render thread, it creates OpenGL, it draws, it lays out, it measures, it handles input events. It's a very scary class. We added a lot of code to that class and we're still scared of it. It's been 10 years, I don't want to open that file.
So the call, and when it gets to the top, it will call over into viewRootImpl, and again, it will call this invalidate child method on that class, which then calls this method called schedule traversals. And this says, OK, something changed that's going to need to go through the traversal process. So it flags that. Traversal is basically all of the phases of measuring and laying out and drawing that handle all of the actual drawing functionality. So looks like that. OK, so we've invalidated all the way up, and now we're actually going to perform traversals. So we're going to perform a draw. We call something like draw at the top level, and that results in a call to get display list. So a display list is a cache of the rendering operations that are responsible for drawing that view.
Right, so earlier I said the draw method, the name is wrong because we don't actually draw. What the draw method does is just records the drawing that you want to do. The actual drawing happens much later. When you run in software, the draw method is executed directly on screen, so it actually draws. But in the case of hardware acceleration, we record everything in those display lists.
All right, so we call get display list. That top node didn't change, so it doesn't need to do anything except just, well, basically call down the tree. It's gotten this invalidation logic in it. It knows that something below it has been invalidated. So when it is asked for its display list, it walks down to its children and says, OK, give me your display list.
And you should start to see a pattern. The only kind of code we write on the framework team is code that goes up and down the tree.
Really good at tree traversal on the framework team. All right, and then we get finally to our item 2 down at the bottom, and we call draw on that to say, OK, well, we need your display list, but that means that you're actually going to need to redraw yourself because you were invalidated previously. So you need to actually re-execute those operations. So that ends up calling into the onDraw method. If you've ever written a custom view, that's what you override to do your custom rendering in your custom view. So in the onDraw method in text view, it does something along the lines of draw this rectangle, which is this background color, and then draw the text.
And this is also where there are big differences with software rendering. When we introduced hardware acceleration, I remember a lot of developers were confused because when Canvas has a get width and a get height method, so you can create the width and the height of the canvas. With software rendering, the width and the height of the canvas were the width and the height of your window. With hardware acceleration, because we record inside the display list, we don't have really a width and a height. So the width and the height of the canvas are just that of your view, because it's independent of everything else on screen.
So these operations into Canvas get turned into operations inside of a display list structure for this view. So basically, we have the equivalent of all the Canvas commands that just records what is the rendering command that needs to happen and the parameters that are associated with it. So we have something along the lines of a rectangle with the current bounds that we need to draw and the fill color that we're talking about. And then something that will also draw the text, in this case, item 2. So we get the display list, and this produces this hierarchical tree of display lists for the entire view hierarchy.
Inside display list, we have private draw methods on Canvas. So we can call Canvas the draw display list to draw a child and make a reference to a child, for instance. And we have a few other things that are not accessible through the public APIs.
All right, so now it's time for the sync phase, which is where we're going to copy information from the UI thread down to the render thread, so the render thread can get on with the job of actually talking to the GPU via OpenGL. So on the UI thread, we have this hierarchical tree of display lists. We sync it across to the render thread, which is a process of basically copying the information that is for all of the views that have changed in this frame. So we copy that over. And we also copy over information about the damage area. Item 2 is the only thing that changed. Wouldn't it be nice if we didn't have to re-render everything for all of the other items? We handle this by passing down the area that needs to be redrawn, and then everything else outside of it can be easily thrown away. In graphics terms, it's called a trivial reject. And in addition to that, we have an optimization to do some bitmap uploading.
Yeah, and there are a lot of things that can happen at the beginning of the frame before we actually start drawing. The OpenGL renderer used by the UI toolkit is fairly complicated, so we have to do things like, if you draw a path, for instance, we don't have GPU support for all paths, like if your path is complicated. We kick off a thread, we do a software rendering inside a special alpha texture, so that later on we can actually draw with that texture on screen. So we do that kind of work at the beginning of the frame. We do the same with font management. We try to guess at the beginning of the frame how much text you're going to need, like all the characters you're going to need to display on screen, and we try to prepare the font cache ahead of time.
I mentioned this a couple of times already. The render thread is responsible for actually talking to the GPU. It's a separate thread because it can perform some operations autonomously and allows things like ripple animations and animated vector drawables to keep animating even if the UI thread is stalled on some long-running operation. All right, so here we are. We have our display list and our damage area, and then we create these display list ops, which is basically another data structure of representing the drawing commands. So we take the information from the display list and we turn it into these DL ops. So we have some information about a clip rect at the top. That's the thing that determines the area that we're actually going to draw into and the areas that we can throw away.
And at this point, we have all the drawing commands in the order that the application has issued them. So here we have a list of items. Each item has a background and a piece of text. So what we see in the renderer is things like fill or draw rect, followed by a draw text, followed by a draw rect, followed by a draw text. The problem with that is on the GPU, whenever we have to switch between different types of draws, so if we have to change the shader, or if we have to change the mesh or the textures, it causes a state change on the GPU. And state changes can be very expensive. And when you have many of them throughout the frame, the GPU will remain idle, and that's not very good for performance. So in this particular case, what would happen is we would have one shader to draw the backgrounds and one shader to draw the text, and we would be ping-ponging between the two if we were to execute all those commands in the same order. So instead, what the render thread does is apply a number of optimizations. One of the big ones is the reordering and batching. So the idea here is to look at all the operations that we want to do in the frame, and as much as we can change their order, as long as it doesn't change the result on the screen, obviously, to minimize all those state changes. Then once we've reordered all the operations, what we can do is merge some of them. So a good example is text. If you have a lot of text on the screen and all that text has the same color and the same font and the same style, instead of issuing multiple draw text to the GPU, we can instead merge them all into a single one, and that's much more efficient for us to send one command to the GPU. There's quite a bit of overhead to calling those OpenGL commands. So the less we can do with the GL driver, the better. We do other things, like if you set alpha on a view, we automatically create a layer. So a layer is a texture in which we redirect all the drawing commands, and then we can composite that texture on screen. And then there's layers, so we have software layers and hardware layers that are under your control. You might have used those APIs on view. You can basically ask us to composite one view and all its children into a single texture, so then we can process that texture as a single draw call. It's useful to do alpha effect or other color filter effect. It's also useful sometimes for performance. If you want to move around a lot of views, you can just freeze them in a layer before doing that.
An added complication that we didn't get into for our simple example is at this time, shadows are also processed. So we have all the information about display lists, and as we turn it into the DL ops, we're checking the elevation of the items. And if they have a non-zero elevation, obviously they're going to have a drop shadow behind them. So we calculate the information for that drop shadow. We combine those shadows for other views at the same elevation, and those become other DL ops that are inserted at the right order.
Right, so and those layers, they're also a state change. So redirecting the rendering into a texture is changing the render target on the GPU, and that's also extremely expensive. So if we kept the layer where they are initially in the stream of commands, we would incur really huge costs. So what we do is we try to find all the commands that belong to a layer, and we move them all to the beginning of the stream so we can prepare all the layers and then draw the frame, draw all the commands that go directly to the screen. So after the reordering and batching, here, for instance, we would do all the draw background first, all the fills, followed by all the draw text, followed by all the draw line. And here's an example of reordering and batching in action. So that's a fairly old GIF showing what happens. So that was Gmail running on a tablet, probably in Jelly Bean. So this is how it would be rendered normally. So you can see that we render every list item one after the other, and within a list item, we render every little piece of image view, every text view one after the other. But you can see that there's a lot of things on screen that are the same. All the C icons are the same, all the yellow chevrons are the same, all the stars are the same, yet we don't draw them together. So after reordering and batching, here's what it looks like. First, all the backgrounds. You see that all the stars were drawn as a single draw call, and the text, we have about 3 different text styles, and we issue only 3 draw text. So much more efficient for the GPU. Here, the app is probably, the fact that we're drawing all the backgrounds one after the other probably means they're overlapping a little bit, which prevents us from merging them. So sometimes in your application, it's not really necessary today, but there are sometimes you can help the reordering and batching by modifying your UI a little bit.
If I recall correctly, I think this single optimization shaved off about a millisecond in rendering time for some canonical Gmail case on a particular device, et cetera, et cetera.
We went from 3,000 GL commands in Gmail to about a few hundred.
Right. So just eliminating all of that, optimizing that specific part of rendering took off a millisecond-ish, which if you think about it, 60 frames a second, you have 16.67 milliseconds. If you can shave off one of those, that's pretty big win and makes it easier to get within that jank-free window.
Right, and in addition to doing the batching and merging, Chet mentioned the idea of rejecting drawing ops that are outside of the clip rect. So because we know the area of the screen that needs to be changed, we can get rid of all the operations that won't be part of that changing area. So here, we clicked one of the items, and after the clip reject, we keep only the drawing commands that match this item. So in practice, what happens is that the reordering, the merging, and the clip rejection happen all at the same time. It's not things we do one after the other. But the goal is always to try to reduce the amount of work we have to do on the GPU or with the OpenGL driver.
All right, so then the next step is we get the buffer. So we need to actually have a buffer to draw these or to issue these GL commands into. The get buffer operation, we put this up there as a separate step, but actually it's implicit in the next step, which is as soon as we start issuing GL commands, then different drivers treat it differently, but basically that's the trigger to the driver to go ahead and provide the buffer, get the buffer at that point, so that the commands have a place to go.
So next we need to turn all those DL ops into actual OpenGL calls. So we're not going to go into details here, but this can be a fairly complicated and expensive step. For instance, if you're drawing a rounded rectangle, what we have to do is look at the paint you're using. From the paint, we create a key. From that key, we generate a shader. So at runtime, we concatenate together pieces of shading code. We generate a program just for that command. Then we have to generate a mesh. So we have to compute the position of a bunch of vertices to create those rounded corners. And then we have to set the state for the OpenGL driver and send that to the driver. So there's a lot of work happening there. Again, we're not going to go into the details, but it's not a trivial step.
And then finally, we're done with all our GL commands. Now we can do a swap buffer, which is us saying, we're done. Go ahead and put the buffer on the screen and do what you need to do to actually display everything.
So we're going to talk about this phase in detail at the end of the talk, but after your application is done rendering, so we do the swap buffer, we need to take all the windows that are on screen and composite them together so that we have a single image on the display. So typically, for a normal application, there will be 3 windows on screen. We have the status bar at the top, we have the nav bar at the bottom, and then there's your application in the middle. By some magic, we send all those buffers to something called Surface Flinger. So Surface Flinger is the window compositor on Android, and there's some complexity happening in there, and then everything shows up on screen. But we're going to talk about this later.
Ta-da. All right, so simple example of just invalidating that one view and everything that happened after that. Let's take a look at a couple of other examples to show you other ways that we handle rendering. So in this case, the user is pressing down, long press, and dragging up. So we're going to actually move the list. So there's sort of two phases of this. One is that it moves slightly, which means no item drops on or off, but everything just shifts vertically as the list is scrolled. And then the user keeps moving their finger, and now there's a new item, this item 6, coming up from the bottom. So we're going to have to do something different there. So we'll take a look at these two separate phases. So in the move only phase, pressed and dragged up, and what happens there? OK, so again, we have the vsync that says, OK, there's some input. Here you go with this information. This comes into an on-touch event as an action down. And we see that the finger went down. Nothing happened yet, but we record where it went down. And that's it. There's nothing else to do with this phase because there's nothing that needs to be re-rendered. No bounds changed. No positions changed. And we're done with this frame. So then the user keeps dragging. So we get another call to that on the next frame. And now we see, given what we recorded previously, in the on-touch event, we know that things have actually moved around. So we walk through all the children. This is code in recycler view, and we offset the top and bottom. So all we're doing is changing the vertical position of these within the container. So this ends up in offset top and bottom, and this is an optimal thing, which instead of doing a standard invalidate, it does what we call an invalidate view property. So the display list that we talked about before, they're mostly these commands of, these are the drawing commands and the parameters that need to be executed to draw this thing. But there's also this little collection of properties in there that are specific to things like the bounds, the left top, right bottom of bounds of the view, as well as things like translation, alpha, rotation. So when those change, then we can just pass those into the display list properties in a render thread directly. So nothing needs to be redrawn. All we need to do is change the display list properties, which is a really quick operation because we're basically just setting some values.
That's what's ambiguous. We don't need to call the draw method on the views. We still need to redraw on the screen.
Yes. All right. So invalidate view property does an invalidate view property for all these things. All of the items got shifted, so they all had their view properties invalidated. We set the values in there. We have that invalidate step, which walks up the tree. But these invalidates are lighter weight in that they are not setting the flag that we were earlier. When we saw invalidation earlier, it was walking up the tree saying, there has been a view in the tree below me that needs to be redrawn. This time, they're just saying, there has been an invalidation of view properties in the tree. They're not setting the redrawing flags. Instead, they're just propagating up the information that says something needs to be redisplayed, but it's a much lighter weight operation in the end. So it gets up to the top. It calls invalidate on view root impl, which says schedule traversals, the standard way of saying you need to do some drawing stuff, get ready for it. It then calls into perform traversals, which does this perform draw operation as it did before. But it has all the display list information. Nothing needed to be recreated as a display list. Instead, all that information is already embedded in the existing display list. So all we need to do is sync the information over to the render thread.
And that sync phase is extremely efficient because the properties that we have for display list, they're just a few numbers. So left, top, right, bottom, alpha, things like that. So we just copy them over. It's just a few bytes per view that we have to copy.
Only for the ones that had changed, which were the 6 items at the bottom there. And then all the steps are the same as what we were doing before. So we won't go into those details because that would take a lot of time. Okay.
But that means that even when we invalidate only the display list properties, we still have to do all the heavy work in render thread. So we still do the reordering, the batching, the merging, making sure the font cache is ready, all that stuff. So there's still a fair amount of work happening.
OK, so now we'll look at the second phase of that scroll where a new item appeared down at the bottom. So again, we process the move. Let's say this is on a further frame when they're dragging further. So again, we end up in an on-touch event, and we realize that things have moved enough that we actually need to make a new view appear at the bottom. So we're going to create that view. We're going to add it into the view group, into the parent, the recycler view parent. And we're going to bind the information in there so that it can display item 6. This ends up in the view group method add view, which does a bunch of stuff. And then it calls request layout. Request layout is basically the layout equivalent of invalidation. It does not actually do the layout. It just says somebody's position or size may have changed in the tree, so we need to walk this up and make everybody go through a measure and layout phase to make sure that everything in the tree is where it needs to be. So that happens essentially the same as we saw for invalidate. So there's going to be a request layout, not on the items, because the item got added to the parent. It's the actual parent that got changed with the new item. So we call add view on the parent, which calls request layout on itself, and then that propagates all the way up the tree.
So a big difference with invalidate. With invalidate, we make the distinction between the view on which we call invalidate, because that's the view that we want to draw, and views that are parents of the view that wants to draw. Chet mentioned that we mark those views in a way so that when we go back down the tree, we can go find the views that are dirty. For request layout, because request layout means that you might have changed the geometry of the view. You might be bigger or you might be in a different position. And that could affect potentially every single view on screen, which is why request layout has to mark every view above as dirty when it comes to measure and layout. We do have optimizations that we're going to mention though.
All right, so gets up to the top, calls request layout on view root impl, which again calls scheduled traversals, because that's what view root impl does. In traversals now, it's going to do a couple of other things that we didn't show you before. Besides the perform draw that we saw before, it also does a perform measure and a perform layout when it needs to, when it was triggered to by that request layout call coming up the tree. So the measure phase is basically asking views, how big would you like to be? What is your preferred size?
Well, it's actually a little more complicated. It's asking view how big they want to be given a certain constraint. So how many of you have ever written a custom on measure method? Just a few. All right, so when you implement on measure, you get measure specs. So measure specs are those constraints. You are told either unspecified, which means you can take as much space as you want, and that's the way the framework uses to know how big does your view want to be, if there was no constraint. Then there's the exactly constraints, which means you have to use exactly a certain number of pixels. And then we have the at most. And at most means I have maybe 1,200 pixels available on screen. How many of those pixels do you want to use to display your content?
Okay, so once we've measured everything.
And there can be multiple measure paths happening. For instance, in a linear layout, we do a first pass where we ask all the views how big they want to be. And if we have space left in the container and we have children that have a weight, we do a second pass to tell them, okay, here's the empty space I have. Do you want to take some of it?
So the typical layout that does multipass is relative layout because everything is dependent upon everything else. So you're pretty much going to hit multipass and relative layout in most situations. Linear layout, it depends on whether you have weights or not. Constraint layout is basically similar to relative layout because of the interdependence of views. And then the layout phase, which is actually cheaper than measure, sets the bounds. So measure calculates how big everybody would like to be and where they want to be positioned. And then layout actually pushes that information into all the views in the tree. So here we have the measure phase. We're going to start at the top with a perform measure. We're going to measure the top one, walk it down all the way, as you would expect.
You can see that at the action bar overlay, there's a branch. We have the action bar content on one side, and we have the content frame layout on the other side. We did request layout, so in theory, the action bar overlay should measure and relay out all the children, because the change in position, the layout param change in one of the children could affect the others. But we do have optimizations in the framework. So when we call measure, we actually remember the constraints that we used the last 2 or 3 times, I think, and we remember the results of those measure passes. And if we see that we're asking to measure a view that did not request layout directly, and the constraints are the same as the last time, then we can just reuse the result that we have cached. This was a huge optimization, and it's extremely useful in layouts like relative layout or constraint layout that do multiple passes, because it allows us to skip a lot of the measure calls.
Let's see, and then we do the layout pass. And the layout pass basically does the same thing. Starting at the top, we push layout down all the way, telling everybody how big they need to be and where they need to be. And now this thing is no longer dimmed out because it is in the right position. Layout has happened, and we're ready to go. So then the rest of the phases for rendering are exactly as they were before, so we won't bother with the details there. Except we lied I had such a simple example, and I didn't want to come up with something completely new just to explain layout, so I pretended like recycler view does a standard layout pass. It does not. Instead, when a request layout comes up to the recycler view, just like list view, it has a serious optimization in it that allows you to be able to fling a list without jank. And that is that when it does a request layout, it knows how big everything needs to be except for the new item. So it figures that out synchronously and just offsets everybody directly. It does not propagate that up. It doesn't force a layout on the entire tree every time a new item appeared. Otherwise, if it did, and when it did in earlier versions of Android,
a long time ago, yeah.
Then you would see janks as new items came on the screen. There are still expensive operations that may be running that could cause that. If they are, then you're doing something at the wrong time. But the framework itself is not causing that problem because we do this serious optimization at that parent level. All right.
All right, so we mentioned composition earlier. You have a number of windows on screen, typically 3 windows. We send them to Surface Flinger, and somehow they appear on the display. So what Surface Flinger sees are actually not windows. They're a thing called surfaces. You've probably seen that term if you use the surface view or various other parts or some of the media APIs. But before we understand what a surface is, we have to understand something even more important in the Android graphics pipeline called buffer queue. Buffer queue is basically the graphics pipeline for Android. So buffer queue is an object that holds onto one or more buffers. When you create a buffer queue, you can specify how many buffers you want. Typically, we'll have 2 or 3. So we say we're double buffered or triple buffered. We're triple buffered when we are lagging behind. So to avoid blocking, we add a bit of latency and we inject a third buffer in the buffer queue. So a buffer queue has 2 endpoints. There's a producer side, and on the left, the green rectangle, and there's a consumer side. So the producer side, that's the part, so the render thread, for instance, on Android is on the producer side. So we said that at some point in the rendering, the render thread gets a buffer from Surface Flinger. It does so by calling DQ buffer. So we're asking the buffer queue to give us one of the buffer it contains. So when we do this, we take ownership of the buffer. Then we can do our rendering. We're going to modify this buffer. It's cut off on the left side, sorry. It just draws inside the buffer. And when we're done, we queue the buffer. So we send it back to the buffer queue at the end of the queue. And then on the other side, the consumer. So the consumer will typically be Surface Flinger to be able to do the window composition, but it could be the media codec, or it could be anything else in the system that needs access to graphics buffer to do something. We'll call acquire buffer. It will take ownership of that buffer. It will do whatever it has to do with it, for instance, window composition. Oops. And when it's done, it calls release buffer and sends the buffer back into the buffer queue. So this is a very simplified version of what happens in practice because obviously we need to synchronize all that stuff. So we have something called the fences, and we have complex mechanisms all across the OS to make sure that all those things happen one after the other and we don't step on each other's toe. A key concept, a key property of buffer queue is that the producer and the consumer do not have to be in the same thread or in the same process. So typically what happens is that the producer is your application inside your application process, and the consumer is Surface Flinger in its own process. And we'll see there are other variants of that. So what happens when you create a window? We have the window manager, and we have Surface Flinger that are separate processes in the system. And window manager is in charge of creating the producers in a way, and Surface Flinger is in charge of creating the consumers. So window manager will first create your window. When you start your activity, for instance, we will create a window. It will also ask Surface Flinger to create what's called a layer. So a layer is effectively the window representation of your activity on the Surface Flinger side. The layer itself creates and owns the buffer queue. So Surface Flinger is the consumer. It creates the buffer queue, and it can acquire and release buffers from that queue. Then the next step is to create the producer endpoint of the buffer queue by creating a surface. And the surface is attached to the window, and that's what your application sees. So whenever your application is drawing, we just enqueue the buffer through the surface. It shows up in Surface Flinger in the buffer queue. Surface Flinger can acquire the buffer and trigger the composition. We use those buffer queues all over the place. So if you use a surface view, for instance, how many of you have ever used surface view? Just a few. Yeah, it's a scary view. It's a very weird view. So here we have a regular activity. So your activity has a surface, that's the blue rectangle. If you were to create a surface view and add it to the activity, we cut a hole through the surface. It's basically just a special rectangle that we give Surface Flinger to tell it to ignore that part of the surface. Then Window Manager will ask Surface Flinger to create a layer. It will create a surface in your process, and you end up with this green surface. And then Window Manager will just slide that surface under your activities window. There are flags on Surface View, it's a little more complicated. You can decide to put the surface above your activity, but most of the time it's just below it. And what's interesting now is that you can have a different producer than the producer that's used for the activity surface. So typically, a producer for a surface view will be OpenGL ES or Vulkan if you do 3D rendering. It could be a media player if you're playing a video. So OpenGL or Vulkan will call DQ buffer, do their rendering, then queue the buffer for that surface. Which means that we can completely dissociate the rendering into the two different surfaces. They don't have to be linked to one another. They don't have to be synchronized in any way. They're completely separate. We have another thing called the surface texture. So the surface texture is a way to create so with the surface and the surface view, we can create the producer side of a buffer queue. With the surface texture, we can create the consumer side of a buffer queue. So surface texture is meant to be used with OpenGL and I think Vulkan in O or soon with Vulkan. So in OpenGL, you would create a texture, and then when you call the surface texture constructor, you can pass the texture ID that you got from OpenGL. What that does is create a buffer queue on your behalf. That buffer queue lives inside your process, and you now have access to the consumer side of the buffer queue. This is exactly what happens with Surface Flinger. When you create a window, remember Surface Flinger creates what's called a layer, and the layer contains the buffer queue. So typically the buffer queue is created in the consumer process. From a surface texture, you can create a surface object. So the only constructor we have on the surface object takes a surface texture as a parameter. And that's how you can give the producer endpoint to your surface texture to someone else. So typically, that would be a media player, another OpenGL engine, or another Vulkan engine. And then what you do on your OpenGL side to consume, on surface texture, there's a method called update text image that will actually do the acquire and release that we talked about earlier. So surface texture is pretty neat because if you're doing custom GL rendering, you can use the surface texture as a regular texture. So you can have a 3D mesh, it can be animated, and on that mesh you can use the surface texture. And the content of the surface texture will be produced by something else. It could be produced by another GL renderer, it could be just a video streaming, it could be the camera. It's made easy with this API. So the main way to use surface texture as an application, if you use the UI toolkit, is to use something called texture view. Texture view was originally created because of the limitations of surface view. So we saw that surface view is effectively a separate window. So if you wanted to do things like scroll the surface view or clip it, it would not be in sync with the content of your application. This has been fixed in N, I think, or O. So that part now works well. But if you need to do other things like rotate the surface view or apply an alpha effect, like you want to fade it in or fade it out, you can't do that because it's not part of your view hierarchy. So instead we have something called texture view.
So actually I wanted to emphasize that. If you were using texture view to integrate it with a view hierarchy so that it would be synchronized better if it was moving around. The recommendation now is to actually go back and use surface view again because now we synchronize the windows. So that should no longer be a workaround, and surface view has less overhead than texture view to integrate with view hierarchy.
So texture view will create the surface texture on your behalf, and the render thread will become the consumer of that surface texture. So internally, that surface texture is treated by render thread like any other texture. So you can think of it as a fancy image view where instead of showing just an Android.graphics.bitmap, you're showing this surface texture thing, which content can be changed dynamically by anything in the system like the camera or media player. So we give you access to the surface texture object, so you can create the surface, so the producer endpoint, and you can give that to any number of the other APIs that we have on Android to produce content. So we have a lot of producers and consumers on Android. We talked about surface view, surface texture. In OpenGL, It depends on the driver, it depends on the GPU vendor, but typically on the first draw call, that's when we do the DQ buffer. So in a Chet section, he was talking about getting a buffer from Surface Flinger. This is actually what happens. We do the driver does this DQ buffer on the first draw. And when you call EGL swap buffers, that's when we do queue buffer. We give it back to the buffer queue. Vulkan works in similar ways, except you have even more control over the queuing and dequeuing. And things like the media codec, so the media encoder is a consumer, the media player is a producer, the camera is a producer. We have a number of APIs that can produce or consume.
It's worth pointing out that one of the ways that you may see this, if you use a tool called systrace, there was a couple of sessions at I/O last year that are on YouTube if you want to know more about systrace. If you see that EGL swap buffers is taking a long time, is that what it's called in systrace?
You see DQ buffer, actually.
DQ buffer.
Q buffer, or, yeah.
That tends to be because you are doing a lot of rendering, or at least a lot of rendering that is very expensive in OpenGL, and so the GPU is having a hard time processing all of that in a quick amount of time. So if there's a stall there, it could be that there's just a lot going on, and it needs to finish all of that before it can actually give you the buffer.
All right, so now that we can consume and produce buffers, let's go back to the composition. So we have a number of layers, they go into Surface Flinger and somehow show up on screen. The way we make that happen is using something called the hardware composer. So the hardware composer is what we call a HAL, or hardware abstraction layer. So the idea is, normally, to composite all the windows we have on screen, we should draw them on top of each other using software rendering or the GPU. But that would be expensive, and we would like the GPU to be used only by the application so you can fully use the GPU for whatever it is you want to do. So to save on battery and to make your applications better, we decided that we wanted to use custom blocks of hardware that are different in every device. So to make use of the custom hardware blocks, we could not, as the Android team, write the drivers for all those different pieces of hardware. So we came up with that protocol that the hardware vendors have to implement, and that Surface Flinger makes use of to do the composition. So we use something called overlays. You can think of overlays as hard-coded, and I say hard-coded, it's actually made of real hardware. It's hard-coded composition. Typically, a device will have about 4 overlays. Some devices, like the Pixel 2, has 7 or 8, which means that the hardware is able to take 4 different buffers and do the composition without using the GPU or anything else, or even running software. So that saves on bandwidth, that saves on power, it's extremely efficient. Now, there are a lot of limitations. So the number of overlays is one, but each overlay can have different capabilities. So for instance, we have devices where the 4 overlays can be scaled and rotated and made transparent. But on some devices, maybe 2 of the overlays can be scaled and the other 2 can be rotated, and only 1 can be 565. It depends on, it changes with every piece of hardware. So to solve that, because we don't know what the hardware can do, we have this very simple protocol between Surface Flinger and the Hardware Composer. Here I'm going to use the original version of the Hardware Composer called Hardware Composer 1. Now we're using something called Hardware Composer 2. But the Hardware Composer 2 has a much more complicated protocol and would have made the slides very complicated to create and to read. So I'm using the old version. So Surface Flinger tells the Hardware Composer to prepare. That's the name of the function. And when we call prepare, we're basically telling Hardware Composer to look at the list of layers we have and to tell us which ones can be handled by the hardware. So in our first use case, Hardware Composer will look at the first layer and say, yep, I know how to do this. It's going to be an overlay. It's doing the same for layer number 2 and for layer number 3. And this is our best use case, and this is the use case that we try to hit all the time, which means that everything, like all the layers, can go directly into those hardware blocks called overlays. So here we're done. Surface Flinger calls set. Set means do the composition. Because all the layers have been marked overlays, we don't have anything else to do on the Surface Flinger side, and the hardware does its magic, and everything shows up on the display. Now, a less common use case, the one we want to avoid, is what happens when the Hardware Composer identifies one or more overlays, but more importantly, frame buffer layers. So frame buffer layers are layers that the Hardware Composer does not know how to handle, and it's telling us that we have to figure out a way to composite them. So here in this example, I said the last 2 layers are frame buffer. So Surface Flinger has to composite them itself. So what we do is, we know we have one layer that can go in the overlays. We will create another layer that we know can be handled by the Hardware Composer, and we have a way of knowing that internally. Then we're going to take our 2 layers that have been rejected by the hardware composer, and we're going to use the GPU to composite them ourselves. So we're going to composite it into that newly created layer. Then we can send all the layers to the hardware composer through overlays and do the composition. And there are a number of reasons why layers could be rejected. What's important to understand here is that it means that every time we add new features to Surface Flinger, we have to make them work on the GPU and also in the hardware composer. If the hardware composer, for some reason, cannot handle a new feature, let's say because it's an older device that was updated to a new version of Android, that means that every time an app or the system uses that feature, we have to fall back to GPU composition, which can be pretty expensive. A good example of that, for instance, recently is color management that we added in Android O. Hardware composers right now are not able to handle multiple color spaces on screen. So if you have 2 windows on screen with different color spaces, we have to fall back to GPU composition for all the windows, and it's pretty expensive.
So here's some miscellaneous things we couldn't figure out how to fit into the slides. There are 2 different invalidate calls. One just says invalidate this view. Another one that used to be an optimization says invalidate the following subrectangle of this view. As of, I think, Lollipop, that functionality went away. Instead, we're going to redraw the entire view anyway. So that one is currently deprecated. Recycler view, besides the optimization of layout that I talked about before, it also does prefetch. So the point where we saw item 6 appear, that item 6 had already been bound and created asynchronously at some point earlier during some idle time due to some new prefetch logic in Recycler view.
For composition, we have the concept of something called virtual displays. It works just like regular composition, except instead of going directly to the screen, we go to a virtual buffer. That's what we use, for instance, when we do Chromecasting to cast to a TV. We use this composition. We also have things like tons of features in Surface Flinger that did not mention, like color transforms that we use to simulate color blindness or to invert the colors for accessibility. Not all hardware composers can support those. And many other things that we don't have time to talk about. So we reached the end. We're out of time, but we're going to be in the main hall to answer all your questions if you have any. And that's the end.
Thanks.
Thank you very much.